In this video, we're going to consider how you work out trigonometric exact values for multiples of the common angles. So the common angles, like 30, 45 and 60 degrees, or the radian equivalent, they're the ones that you should know kind of off the top of your head. But what happens if you have to work out something like the sine of 225, which is a multiple of 45, or the cosine of 2 pi by 3? So there are multiple methods for this. I'm going to use the cast diagram. Hopefully you're familiar with the cast diagram. So what we do, we start by just marking up a cast diagram, just like you would normally use the cast diagram in trigonometry. Remember, it starts here from 0 going counterclockwise. So this is the C quadrant, A, S, and T. Just take the angle you're interested in, 225 in this case, and mark it on the cast diagram. Remember, you're rotating this way, so 90 degrees, 180, 225 would be somewhere like here. So that rotation there is 225 degrees. But the important thing is, whichever quadrant we've ended up in, this time the T quadrant, there's going to be a new angle in there, which in this case is 45 degrees. So it's 180 degrees to there, but 225 to there. So that leaves an angle in there by simple geometry of 45. As soon as you get that new sort of reference angle, it means that this original calculation, the sine of 225, can then just simply be made into the sine of 45. So you're just transferring the problem from something you don't know to something you do know. And this new angle will always be either 30, 45, or 60 degrees, or the radian equivalent, because those are the angles that you're meant to know the exact values for. So one thing to note with this, it's always the angle here rather than the angle here you make. So it's the angle touching the horizontal axis, okay? But the reason we put it on a cast diagram, notice we've ended up in the T quadrant, and in the T quadrant, the sine function is negative. So not only is it the sine of 45, it's a negative of the sine of 45. Sine of 45 is 1 over root 2, or root 2 over 2 in its rationalized form. So that's just going to be minus 1 over root 2, or minus root 2 over 2. So that last part, the sine of 45, 1 over root 2, you should just know that. That's one of the exact values. Okay, so we're just transferring the problem from one angle onto another, to an angle that we know. The same method works in radians. So a lot of students like to convert radians to degrees. To be honest, I like to convert radians to degrees. They're just easier to generally work with. So pi over 3, 180 divided by 3 is 60 degrees, times 2 is 120. So this statement here is just the equivalent of the cosine of 120 degrees. That's not a value we know off the top of our heads. It's not an exact value. So we're going to go through the same method here. So again, just fire up a little cast diagram. Doesn't have to be too pretty, doesn't have to be artistic, just a quick representation. So again, starting here from 0, marking on 120, so 90 degrees to there, 120 would be to like here somewhere. Yeah, somewhere like here. So that there is a rotation of 120 degrees. That then, by simple geometry, is going to leave, that's 180, so that's going to leave a gap here of 60 degrees. So that 60 degrees becomes our new reference angle. So that tells us that this is equal to the cosine of 60 degrees, which is one that we know. So again, though, be aware of what quadrant we're in. We're in the S quadrant, the sine quadrant, where cosine is negative. So again, we need to put a little negative in there. If we had rotated all the way through to the C quadrant, where cosine is positive, we wouldn't need a negative. So it's only if you land up in a quadrant where the function is negative that you need a negative. Similarly, if we were in the A quadrant, then we wouldn't need a negative either. So the cosine of 60 degrees from exact values is 1/2. So this becomes minus 1/2 as a final answer. So that's how you work out trigonometric exact values for multiples of the common angles. In this video, we're going to consider derivatives and integrals for trigonometric functions. In particular, trigonometric functions in this form, which often cause confusion for students. But the key is, let's say you had a trigonometric function in this more basic form, like sine 4x or cos 2x, so sine or cos number x. Well, how do we differentiate or integrate that? Well, we use the chain rule, don't we? Because this is a composite function. The function 4x is inside the sine function. Or if this is on a formula sheet that you get as part of your course, then that is just going to be a direct, pull off the formula sheet. So we would differentiate this by saying, okay, well, when you differentiate the sine function, that goes to cosine, positive cosine. So it'd be like this. So cosine of 4x. A good tip is that the part in the bracket for all of these never changes, okay, so never try and change the inside of the bracket, but because this is the chain rule, that's our first derivative, and our second derivative, if you like, is the derivative of the inside of the bracket. That's always how the chain rule works, so it's going to be this multiplied by 4. But most students don't even write that, and you don't have to write that. They can just look at that or refer to a formula sheet and realize that the answer is going to be 4 cos 4x. They sometimes forget that this 4 is a derivative of 4x, but the key thing that we're focused on here is that the number that we multiply in front is the derivative of the inside of the bracket. Now that's the key for when you get to these more difficult scenarios, because most students are okay with this scenario, derivatives or integrals of something that look like that. And by the way, the integral case would be if we were integrating sine 4x. Again, very similar process, but instead of multiplying by the derivative, we also use the derivative, but we divide by it. So sine integrates to negative cosine, so this would be negative cosine 4x, and then we're dividing by the 4, and we usually just write that as a 1 over 4 in the front, and because it's an indefinite integral, we need a plus c on the end. So when we come to this case here for the derivative, or this case for the integral, in both cases like this one over here, we're still using the derivative of the inside of the bracket. So in this case here, let's start by considering the derivative of this. Well, 3x minus pi over 7 looks a lot more complicated than just 4x. But what is pi over 7? It's just a number, right? So if you differentiate 3x minus some number, you just get 3. Because when you differentiate a number, even if it's a fancy number and it's got a pi in it, it still goes to 0. So the derivative here is still just 3. So when we take the derivative of that overall function, it's actually not that dissimilar to what we did here. So we can say, right, when you differentiate cosine, that goes to negative sine. The 2 is just going to stay as a 2. So it's going to be negative 2 sine. The bracket, like I said earlier, never changes. So we leave the bracket. And then we're just going to multiply that by whatever the derivative of that is, which is just the number 3. So nothing fancy, very similar to this case. We can then tidy this up by multiplying those together, or if you're confident, you can go straight to this final form from here. Minus 2 times 3 is negative 6. So it's negative 6 sine, and then again, the bracket never changes. Okay, so this case, it looks a lot different to this one, but it's actually very similar in how it works. Let's take a quick look at the integral. Same idea, just that we're dividing by the derivative. It's the same function actually, so the bracket again never changes. When you integrate cosine, that goes to positive sine. The 2 is just going to stay there, so it's going to be 2 sine, and then the bracket will stay the same. 3x minus pi over 7. This time we're dividing by the derivative. The derivative is still 3, so we would divide by 3, or you could just write it as 2 over 3 like that. Because it's an integral, an indefinite integral, we're going to put our plus c on the end. So in all of these cases, which are all examples of the chain rule, we're just using the derivative of the inside of the bracket. If there's a pi over something, plus or minus pi over something, that doesn't play any part in the derivative, it's just a number. So it's only this number here that you're going to be multiplying or dividing by. In this video, I want to look at some examples of the chain rule for differentiation. So most students are okay with the chain rule for differentiation in certain forms, but when the situation varies, they get a little confused or they slightly do the wrong thing. Let's start with the most basic form, which is a bracket with a power, and the inside of the bracket in this sort of linear form, which is number x plus or minus a number. When you start the chain rule, that is usually the first form that you see, and that's still usually the most common form. So there are different ways to think about how to go about this derivative, but essentially all versions of the chain rule say that you need two derivatives. You need to differentiate the overall function, whether that's a bracket or a trigonometric function or something else, and you need to multiply that by the derivative of the inside of the function. That is all that the chain rule is, two derivatives multiplied together. So if we differentiate this overall function, we can do the bracket, sorry, we can do that by using the power rule. So you bring the power in front, so it's going to be 4. The bracket never changes in the chain rule. Reduce the power by 1. So that's just normal differentiation. The thing that makes it the chain rule, we're then going to multiply by the derivative of the inside. The derivative of 3x minus 2 is just 3, like this. And then we can take an opportunity to multiply these together to make the final form 12 bracket 3x minus 2 cubed. So when most students learn the chain rule, they practice things that look like this, and they get very used to putting a number here on the end. So bracket times number, and they might do that 50 times, right, to practice it. So they get very used to that. But it's not always a number on the end, because remember, this thing on the end, this thing here, is just whatever the derivative of the inside of the bracket is. So yeah, sure, a lot of the time it is a number, but you've got to keep in mind it's a derivative. So in cases like this, where the derivative of the inside is a little bit fancier, it's not just going to be a number, it's going to have x's in it. But let's just go through the same process. So if we want to take the derivative here, going through the same steps, we bring the power in front, we leave the bracket alone, we reduce the power by 1, so that's the first derivative, and then we multiply by whatever the derivative of the inside of the bracket is. In this case, the derivative of 3x squared minus 2 is 6x. So it's not just a number this time, it's got an x in it. Still do the same thing, multiply these together, so we're going to get 24x, 3x squared minus 2 cubed. Okay, so different forms, subtly different. All that's happened here is I've made my 3x into a 3x squared, but it's changed the way you need to think about the derivative slightly. This form here, just another example. So we can go through similar steps. So f dash x here, bring the power in front, leave the bracket alone, reduce the power by 1, and then just multiply by whatever the derivative of the inside is. If it's a number, great. If it's not a number, just use it, whatever it is. So the derivative of x to the power of 4 is 4x cubed, like that. So that's the second derivative in this case. Multiply those together, so we're going to get 12x cubed, bracket x to the power of 4 plus 1 squared. So the key takeaway from this video is that, yeah, often the end thing will be a number, but often this thing on the end is also not a number. So just be aware that it's always just the derivative of the inside of the bracket that you're multiplying onto the end. A question like this would give you a graph, and it would say something like, find the equation of this curve, what is the equation of this function, or something like that. In other words, here's a graph, what is the function? These questions, in my experience, tend to be really poorly done. They're generally done okay if it's a parabolic graph, so a quadratic function, but when you move up to some other type of polynomial, like a cubic in this case, they tend to be poorly done. And they tend to be poorly done because students don't remember the general formula. So the general formula for a cubic function, now remember that a cubic function is one that contains an x cubed term. If it contains some other highest power term, like a power of 4, that would be a quartic, a power of 5 is a quintic, and they just keep going like that. But let's focus on the cubic case, although this would be applicable to other cases as well. In the case of a cubic, the general form is going to be some k value in front, which is a coefficient value, multiplied to 3 brackets. So when you factorize a polynomial function, the order, which is the power, the highest power, dictates how many brackets you should get. So a cubic, being a power of 3, should have 3 brackets. So the general form is going to be something like this. 3 brackets, potentially some number in front, which is often a 1, but it can be something else. But the other important point is that each of these brackets, each of these factors, relates to one of the roots. And essentially the a, b, and c value reflect the root points on the graph. And that's always true for polynomial functions in their factorized form. Just like if you had 2 brackets, you would know that these 2 numbers, the b and the c, relate to the 2 root points. So it's the same with a cubic function. But in the case of a cubic, it does potentially get a little bit trickier, because I'm claiming that there are going to be 3 brackets, but we can see here that there are actually only, well, there are 3 brackets, but there are only 2 roots, and I'm claiming that each bracket connects with one of the roots. So it kind of does, but there's a little twist to it, and the twist is the thing that often gets students a little confused. So we can see we've got a root at -1 and a root at +2. So the -1 root just needs to have a factor that goes with that. So if it's a -1 root, it's going to be an x plus 1 factor. And if it's a +2 root, it has to be an x -2 factor, because the sign in the factor inside the bracket is always the opposite to how it is on the root. And that's because if you were to put a 0 there for y and then solve that equation, you would be flipping the sign on the other side. So we've only used two of our brackets, and this is how you will, by the way, start these questions, by knowing the formula, associating the roots to the factors, just to fill in the values. But notice that we should theoretically have a third bracket. We don't have that. That's because this root here is also a turning point. If you've got a root which is also a turning point, which is a super common scenario in this type of question to try to test the student's knowledge a little bit more, then essentially what happens there, that factor gets repeated like this, okay? Or you could write it with a bracket once with a squared on it, that's fine as well. So either that form, or probably more commonly would be this form, just to write that bracket one time and put a squared on it. So it's still the case that we're associating the roots to the factors, but if it's a turning point also, you need to repeat that factor. Usually there'll be another point given in these questions. In this case, it's a y-intercept point. It doesn't have to be the y-intercept, it could be any point, but this additional point is for finding the k value. So that point there at -8, just remember the full coordinate of that point is 0, -8. So 0 is the x value and -8 is the y value. If we substitute those into the equation, we get -8, k is just k, x is going to be 0, so that's going to be 0 plus 1, and then 0 minus 2, and essentially we've now made a little equation, and if we solve that equation, we'll get our k value. So let's just quickly develop that. So k can just stay in front, 0 plus 1 is just 1, 0 minus 2 is -2 squared, keeping the -8 there, -2 squared is +4, times 1 is still +4, times k is going to be 4k, so that gives us a k value of -2. So the additional point you get in these is nothing to do with, it's not a root point, so it's nothing to do with the factors, it's just to do with finding the k value. So then we could go back to this point here and just finally say that the equation is -2 for the k value, x plus 1 for the first factor, and then x minus 2 squared, repeated factor, for that turning point root. So that's how you find the equation of a cubic function from its graph. In this video, I'd like to look at trigonometric identities proof style questions, a question that would be worded show that something is true or prove that something is true. Essentially in questions like this, I give you an expression equal to something. So this one was equal to sine cubed x, or this one was equal to 1 minus cos 2x. And they want you to basically turn the left-hand side of the expression into the right-hand side, so to prove that those two things are equal, or to show that they're equal. These questions are not particularly popular among students, and part of the reason for that is, well, other than the fact that they're very difficult, is the fact that they're never the same. You know, there's no standard method for these. And when students come across problems where there's no standard method, it can be a little frustrating, right? Because it takes experience and a little bit of insight. But in this video, rather than just going through these problems, I mean, I am going to go through them, but rather than just go through them, I want to share a couple of tips in terms of strategy. So I would say that 90%, if not more, of these problems contain a sine 2x term and or a tan x term. The sine 2x formula, the double angle formula, is on the formula sheet, and the reason why they choose the sine one rather than the cosine one, there's only one sine double angle formula. For a cosine 2x, there are 3 formulas. If you put a cosine 2x into one of these problems, it's very difficult for students to pick out the correct formula. It would be difficult for me, in some cases, to pick out the correct formula. So basically, if you see a sine 2x, it is a no-brainer that you should just change that using the formula sheet. You might even get a mark for that already, but look out for that because it's almost certainly going to be there. The same with the tan x. If there's a tan x, no-brainer. You're changing that to sine over cos, which is one of the identities that's not on the formula sheet. So scanning our original problem here, there's a sine 2x, so just go yourself, right, no-brainer, sine 2x, changing that to whatever's on the formula sheet, which is 2 sine x cos x. Only make one change per line, right? So you're just changing out that term, not doing anything else, but that is going to be the key to getting going in these questions. Once you make a change, look for any simplification, because often after you change something, the algebra, the structure of the algebra then changes. So notice that this fraction now has got a 2 on the top and the bottom, so we could cancel those. It's got a cos x on the top and the bottom, so we could also cancel those. So that's going to leave us with sine x minus sine x cos squared x. One other tip, a second tip, apart from looking out for the double angle or the tan x, look for the other, or remember that in general, you're going to use one of the other trig identities. So the other identities are sine over cos equals tan, or sine squared plus cos squared equals 1. So taking for a moment that second formula, so sine squared x plus cos squared x equals 1, just keep in mind that this formula can be rearranged, and it's usually the rearranged form that we use. So for example, here we've got a cos squared x term. We don't have a sine squared plus cos squared, we've just got a cos squared. But if we rearrange this formula for cos squared x, we would get 1 minus sine squared x. So that's another thing to look out for in these, pulling in one of the other trig identities. If we then go ahead and replace that term, remember to keep everything else the same. So I'm not changing those, only the cos. I'm changing it into 1 minus sine squared x. So I'm taking this cos out, replacing it with this guy here. So bracket, need a bracket because there's two parts to this expression. So bracket 1 minus sine squared x. And that gets us well on our way. And the rest is just basically going to be algebra. I'll just quickly finish this one off. So sine x, now we're going to expand the bracket. Sine x times 1 is just sine x again. Minus minus makes a plus. Sine times sine squared gives you sine cubed x. And then these two guys here would cancel to leave you with just sine cubed x. Not too worried about the answer here. I'm more worried about the strategy. So looking for the double angle, looking for simplification, looking to use another formula. This one here, again, no brainer, that the sine 2x should be made into 2 sine x cos x. If you see a tan, it's pretty much also a no-brainer. You're going to use the other formula from the formulas that are not on the formula sheet, so this one and this one, to change the tan to sine over cos. So you probably, again, already got a mark for that. Now you're just looking for simplification. There's a cos here on the top and one on the bottom, so they're going to cancel. That's going to leave you with 2 sine times sine, which is 2 sine squared x. This one is a little bit more difficult to finish off. We were trying to get to 1 minus cos 2x. So different ways you could finish this one off, but on the formula sheet, one of the formulas for, let me just put it here, one of the formulas for cos 2x says that cos 2x is equal to 1 minus 2 sine squared x. Okay, now this one is on the formula sheet. If you rearrange that by taking the negative 2 sine squared term to this side and taking the cos to that side, you would end up with positive 2 sine squared x equals 1 minus cos 2x. Meaning we can then just take this, which is here, and replace it with that guy there. So that's going to give us, I should really have some equal signs in here, that's going to give us 1 minus cos 2x. And that's the final form. But again, I'm not too worried about the final form. I'm worried about how do we get going in these questions, which is to look for the double angle, look for the tan, and then substitute those into your expression. Tricky questions, but I hope those little strategy tips maybe help. You sometimes see questions which give you a function and they ask you to evaluate this expression here. F to the minus 1 of f of x. Or the other way around, it can be sometimes written as f of f to the minus 1 of x. In other words, we're asking you to compose the function, make a composite function between the function and its own inverse, or the inverse and the function. These questions are normally worded state or write down, and they're usually only 1 or 2 marks, usually just 1 mark, because you can write down the answer. But let me just show you what happens here. So if we actually go through the process, it doesn't matter which way you compose these. Let's say, for example, well, in either case, we need to find the inverse first. So let's start by finding the inverse, which is a separate technique. So to find the inverse of this function, you take the f notation, change it to a y. That's just purely to allow us to do some algebra. We tend to just not do algebra with the function notation. And then making the inverse is essentially changing the subject of the formula to the other variable, so x in this case. So if I add 8 to both sides, I will get y plus 8 equals 3x, and then divide both sides by 3, and I would get x equals y plus 8 over 3. And that would tell me that the inverse, f to the minus 1 of x, is going to be equal to x plus 8 over 3. So that's a technique for finding the inverse. So that's a function, that's the inverse. If we want to compose them, so let's say we want to do this guy here. So that's a function composed with its own inverse. So that's a function And then the internal function is x plus 8 over 3. So just replacing that f to the minus 1 of x with x plus 8 over 3, because that's what that function actually is. That's how we go about composite functions. So what does that then tell us to do? It says, now you look at the f function, which is this guy here, and everywhere there's an x, you're going to replace it with this guy here. So we've got 3 times x, so it's going to be 3 times this guy here, which is x plus 8 over 3. And then we've still got this minus 8 on the end there. So multiplying the 3 into the bracket, well, you could multiply into the bracket, or just notice that the 3 outside and the 3 inside the bracket, essentially, because one is on the top and one is on the bottom, they're just going to cancel. So that's just going to end up with x plus 8 minus 8. The two 8's also cancel, and you just get x. In other words, if you compose a function with its own inverse, you get x. And if you compose the inverse with the original function, you also get x. And that makes sense, right? Because a function and its inverse, they do the opposite things. So whatever you're doing to the x by this function, you're undoing it with this one. And whatever you're doing to the x by this function, you're undoing it with this one. So if you ever see this question here, don't waste your time making the inverse and then composing it, which would take potentially 2 or 3 minutes. You can just state the answer, which is just x. And that's how the question will be worded, and that's why it's only a 1 or 2 mark question. Questions referring to the domain of a function are not very popular with students because they're a little bit icky, they're a little bit tricky, and students are not always sure what the question's asking or what they're really looking for. But essentially, every function has got a domain, and the domain are the values you're allowed to put into the function without there being some kind of problem. The opposite of that are the restrictions on the domain. The values, if you do put them into the function, are going to cause some kind of issue. There are only 2 potential issues with the domain of the types of functions you're going to see. One is dividing by 0, because you can't divide by 0. That's not an operation you can perform. The other is square rooting a negative number, which is another operation that you can't perform. So those are the only 2 possible scenarios that can really have an impact on the domain. So keep that in mind first of all as you're doing a domain question. Of the 2, the dividing by 0 is the more common scenario. So let's say you got this function here and the question said, what values cannot be in the domain? Or what values, or what are the restrictions on the domain? Like, what are the values that are going to cause a problem? Well, there's no square root in this question, so the square root issue cannot be part of the problem. The only problem could be if the denominator was 0. So you're trying to find the x values and make that denominator 0. Now, most students will look at this and they'll start trying to guess values or guesstimate values or work it out in their heads. You can get there eventually, but you probably wouldn't even get the marks for that anyway, or you might get possibly 1 mark. But an easier way to do it is just say, well, if I want to find the values that make that 0, let me just take that denominator, which is quite often a trinomial, like this one, set it equal to 0. If I set it equal to 0 and solve that quadratic equation, those are the values that will give me 0. So this is the formal way to do it. Set it equal to 0. Because it's a quadratic equation, we need to factorize it. This one would factorize like this. And then you're going to get solutions for the equation of x equals 4 and x equals 3. So to answer the question, what values cannot be in the domain? What are the restrictions on the domain? These 2 values. In other words, if you put 4 in there for x, the denominator will be 0. If you put 3 in there for x, the denominator will be 0. So that's how you would find the restrictions in that case. In this case here, slightly different because, well, first of all, we're dealing with the square root. Secondly, we are also dealing with the fraction issue, but just dealing with the square root first of all. So let's think about the values that would cause a problem here. So if x was 4, 4 take away 4 is 0, you can square root 0. You get the square root of 0 to be 0, so that part's okay. But in terms of the square root part, any number that is smaller than 4, like let's say for example that x was 3, then 3 take away 4 is minus 1, then you'd be square rooting a negative. But even if x was say 3.9, then you're still going to have a problem because you would get a negative when you subtract 4 from that. In fact, if x is any value smaller than, if x is smaller than 4, you're going to get an issue because you're going to be trying to square root a negative. If x is 4, like I said earlier, the square root part's okay, the square root of 0 is 0, so you can process that square root, but then you would be dividing by 0. So that means that the problem parts of this function, the parts that cannot be in the domain, the restrictions, are where x is smaller than 4, or in this case, equal to 4. They're both going to cause a problem for different reasons. One, for square root and a negative, and secondly, for dividing by 0. The main questions can be difficult to navigate, but I would say in most cases, look out for the dividing by 0. It does tend to be the predominant feature, and look out for the bottom, the denominator being a quadratic, particularly a trinomial, but could be a binomial, but something you've got to factorize and then solve. Those will be the restrictions on the domain. In this video, we're going to consider how you solve a quadratic inequation, which is a quadratic expression. Instead of being equal to 0, it's greater than or less than 0. It's a similar technique in some ways to solving a quadratic equation, but it also differs in some ways. So it starts off in the same way, in the sense that you're going to take this expression and factorize it, but you've got to be careful not to try and mimic a quadratic equation too closely. So the first thing is, like a quadratic equation, the terms have got to be on one side and it has to be a 0 on the other, regardless of whether it's less than or greater than 0, but all the terms have to be on one side. If one of these terms was on the other side, just like a quadratic equation, you've got to bring those terms all to the same side. So this is set up ready to go. It's in the correct format. We're going to factorize this. It's a trinomial in this case, so it's going to factorize into 2 brackets. This would also work if it was a binomial. You could just factorize into 1 bracket. For example, if there was no 9 there, you could use a common factor of x. So in this case, it will factorize as an x, a 9 and a 1, and we need 2 negatives. In the case of a quadratic equation, let's say that we had now x minus 9, x minus 1 equals 0. In this case, we would separate that off into 2 little mini equations, x minus 9 equals 0, x minus 1 equals 0, and we'd solve those to get 9 and 1. The 9 and the 1 that we've solved for, they're the solutions to the equation, but they're also the roots of the graph. So this is what we do in the equation case. The thing that most students want to do in this case is to mimic this. So let me show you here what not to do, but what most students do. Most students will say, okay, well, I'm just going to take x minus 9, and like this part here, I'm going to make its own little equation or inequation, but I'm going to set it greater than 0 because it's greater than. And I'm also going to take x minus 1 and make that greater than. Now, why is that a problem? Well, it's a problem because we've got 2 things multiplying here. A bracket and a bracket means multiply. We're saying we're multiplying 2 things together to give you a result which is greater than 0. In other words, a positive. But when you multiply 2 things to get a positive, either they're both positive, like this, or they're both negative. We don't know which one's which, and we can't tell by the algebra which one's which. So we don't do it like this. So this is the thing to avoid. What we do instead, we do a little bit of side working like this to get the actual root points. Or sometimes usually you can just tell what the root points are going to be, so 1 and 9, just by flipping the signs. And we're going to use these 2 root points to sketch a graph of the parabola. Remember, this is a quadratic function, so it would make a parabolic shaped graph. So we just take a little sketch, doesn't have to be too fancy, roughly mark on where 1 and 9 is. So 1 is going to be approximately there, 9 is going to be there on the x-axis. This is an x squared with a positive x squared, so it's going to make a u shape rather than an upside down u. But look out for that in this question in particular. It's really important to get the shape correct. So our parabola would go something like this, right? Through the 2 root points to be something like that. Now, why do we use the graph? What do we need to do on the graph? Well, this is saying our quadratic, our function, our parabola has to be greater than 0. Greater than 0, positive, means a part of the graph above the x-axis. In other words, this part of the graph here, this part of the graph here, remember that carries on forever, but not this part of the graph here, because that part is below 0, less than 0. That would be the part we would look at if it was the other way around. This point, remember, was at 9, this point was at 1, so we want all the part of the graph which is to the right of 9, and all the part of the graph which is to the left of 1. Capturing that mathematically, that would say all the x values that are greater than 9, and this part would say all the x values that are less than 1. And those are the solutions to the question. These questions should be worded not find the value of x, but find the range of values of x. these are the two ranges that they're referring to in the question. If this had been the other way around, if it had been set less than 0, we would be focusing on this part of the graph. If it's this part of the graph which is continuous, whereas these two parts are discontinuous, in other words, there's a gap between them, if it had been that part, you could set up your final answer like this, where it would just need one range of values, and it would be all the values between 1 and 9, so it would be like that. So if it's going to be two parts, probably just separate them. If it's going to be one continuous part in the middle, you could write it like that. But that's how you go about solving a quadratic inequation. Where do these come from? Well, many sources, but particularly from the discriminant. If you get a discriminant question, b squared minus 4ac, and they tell you that it's got no real roots or two real roots, then that's going to be either greater than or less than 0. So that would end up giving you potentially a quadratic expression greater than or less than 0. That's quite often the source of a quadratic inequation question. In this video, we're going to consider how you write a trinomial in completed square form if you've got a coefficient other than 1, in other words, some number in front of the x squared term. If there's no number in front of the x squared term, this process is significantly easier, and the process you would use in that case, we still need to use in this case, but there's some added steps that need to go in. In fact, in that simpler case where there's no number or a 1 in front of the x squared, it's really only a one-step or maybe two-step process. This technique, though, needs several steps of working, probably 3 or 4, maybe even 5 steps. So the big mistake that I see students make in this technique is that they try to do too much in the first step of working. The first step is simply to pull out the common factor between the first two terms, but only the numerical common factor. Often these questions are set up with two numbers here and here, which have got a common factor, but the third number, the n number, doesn't share that common factor. If it did share the common factor, then you could pull out the common factor of all of them, and then that would be a slightly different problem. So look for the common factor, but it's only the numerical common factor. We're ignoring the x common factor. So the common factor here is 3, so I'm going to pull out a 3. I'm then going to use a square bracket. That's a common form for these. So 3 bracket x squared plus 4x plus 17. But that's the step that most people miss. But you've got to get that step. If you don't get that step, the rest is not going to work out very well. So you're basically ignoring the term on the end. It's the next step that really is the completing the square part. So we're just leaving the 3, the common factor, we're leaving the square bracket, and we're leaving the 17 on the end. We want to do completing the square on x squared plus 4x. So this is where you need to know how to do completing the square, which is where you take the coefficient of the x and half it. So like that, x plus 2, put a squared on the bracket, and then you're always going to subtract the number from that, okay? So after the bracket. And you're going to subtract whatever number you've just put in the bracket squared. So in this case, it's going to be minus 4 like that. And then we expand the square bracket. So the 3 has to multiply to this, and the 3 has to multiply to the minus 4. But when you multiply the 3 to this, you can't actually multiply it into the bracket because it's got a power on it. So we're just going to put the 3 in front of the bracket. So 3 bracket x plus 2 squared. 3 times minus 4 is negative 12, and then we've got the 17 on the end. And then you can just tidy up the end numbers like this, and then that's going to give you a plus 5 on the end. So I'm just going to run through another example. This one's got a negative 3 in front of the x squared. It doesn't really change the process, so we're just going to pull out that common factor, which in this case is negative 3. You could use 3 as well, but I would recommend using the negative. So negative 3 square bracket x squared plus 2x like this, plus 7. Again, the end number is just hanging out on the end like that. Keep the square bracket, and then we're going to do completing the square on the inside of that square bracket. So that's going to be x plus 1 in this case, all squared. Taking away that number squared. So 1 was in the bracket, so we're taking away 1 squared, which is 1. Just like here, we took away 2 squared. Then just multiplying into the square bracket. So minus 3 times the round bracket. Again, you can't multiply into that round bracket, so just writing it like this. Minus 3 times minus 1 is plus 3. Keep the plus 7 on the end, and then you can just combine those n numbers, so to give you a plus 10. So that guy there and that guy there are the same thing, just written in a different way, in the same way that that guy, the original trinomial, and that guy there are the same thing. The absolute key with this question type, undoubtedly, is that first step. Got to get that first step right. If you just pull out the common factor, the rest can flow. If you try and do too much on that first step, it makes the rest of the working sort of unrecoverable. So that's how you complete the square for trinomials, which are in that particular format.